Okay, so in this part we're going to define magnetic flux. Now, we've taken before already in chapter on Gauss's law what electric flux was. It was this abstract quantity that you defined over a mathematical surface. And it's the same thing exactly for magnetism. So if you take a mathematical surface, this surface does not exist in nature. It's not made of any material. It's an imaginary surface in space. It could be any shape. It doesn't have to be flat. It could be any shape. And if you cut up this area into small elements of area, like small squares for instance, this is one of those small squares, then you can define an area vector to be perpendicular to that certain particular square. And that vector, the direction of the vector, it's perpendicular to the area. And of course for an open surface, as before, there's always a confusion. Should you make the area vector pointing this way or should you make it this way? So you have to make a choice for an open surface. You have to choose. But if you choose one direction for this area, you choose the same for the other ones. So in this case, we choose to make the area vector point perpendicular this way. The value, the length of this vector is the actual area of this square. It's just this distance times this distance. And the direction is given as to be perpendicular to this small square. And then, of course, before, the elements of area, different elements of area could have different area vectors because the normal is different at different locations on the surface. And so that's something we've discussed before in detail on Gauss's law. If you don't remember that in detail, go back to Gauss's law. Now, what if you put a current distribution? For instance, get a wire that has some current in it, and it's making a closed loop like this. Of course, this wire, because it has a current in it, it'll make a magnetic field in the region of space. And so if you go now to every square, you have two vectors defined at every square. You have the area vector, but you also have the magnetic field vector at that location. And so we define magnetic flux for this particular element of area to be the magnetic field dotted into the area vector for that particular point at the center of this square, which means the magnitude is bi times the magnitude of the area times cosine of the angle between them. And so that's what the flux, magnetic flux through the element of area is defined to be, B dotted into the area, which is B delta A cosine theta. And of course the magnetic flux doesn't have to be the same for every area because the area vector points in different direction than the magnetic field. The angle is not the same everywhere. The magnetic field is not the same everywhere. So in general, the flux through each of these areas could be different. And we also remember that the flux, it's a number. It's the dot product between B and area. So it's a number. It's either positive, negative, or zero. And if you want to then define the total magnetic flux through the surface, you add the dot product for all the elements of area, letting the size of the area element go to zero, and which is basically integration of B dot dA. So it's identical to the definition of electric flux, but now instead of the electric field, you're putting the magnetic field.